In this video, I'll define a few new terms for commutative rings R. So let A, B, and P be in your commutative ring. Then my first definition is A divides B if there is a C in my ring with A times C equaling B. We understand the idea of divides for integers. I'm just defining that idea for an arbitrary commutative ring. So U in the ring is a unit if U divides 1. So that means there's an element C in the ring such that U times C is 1. In other words, U has a multiplicative inverse. So U inverse exists. So the units in your ring R are the elements that have multiplicative inverses. The third term I'd like to introduce is A and B are associates if A is U times B for a unit U. And then the last definition is irreducible. So P in my commutative ring is irreducible if P equaling AB means that A or B is a unit. So that's the concept of an irreducible element in a commutative ring R. Okay, let's do some examples. So let's consider first good old integers. The units are plus or minus 1. Those are the only elements that are integers that have multiplicative inverses. The irreducibles are plus or minus the primes. If you have a prime number and it's written as a multiplication, A times B, then either A or B has to be plus or minus 1. That's even the definition of a prime. So integers are a comfortable ring. Let's do another example that we've seen before. How about we consider the ring of polynomials with rational coefficients. So the units are all the elements in this ring that divide 1, all the elements that have multiplicative inverses. I think any rational number besides 0, so I denoted Q star as the set of Q with 0 thrown away. These are the units. And the irreducibles are the irreducible polynomials. We've studied irreducible polynomials before. Those are the irreducibles in this ring. I'd like to do one final example, a more interesting example that we haven't quite seen before. These are the Gaussian integers. It's an interesting ring. It's the ring of integers adjoined an extra I. I is the complex number, the square root of -1. You could think of it, I'm using the same notation here for polynomials. You could think of this as polynomials with integer coefficients in I, but if you have I squared, you could write it as -1. So no polynomial other than degree 1 would exist. In other words, you get the ring of elements of the form A plus BI, where A and B are integers. So these are the Gaussian integers, and you can plot the Gaussian integers in the complex plane. So I'm going to do that. I'm going to plot a bunch of Gaussian integers here. So I have a real and a complex axis. This is the complex plane. But to be a Gaussian integer, your coordinate has to be integers. So here's my real axis. Here's my complex axis. This is the number 1, 2, 3, and so on. This is here, I, the complex number 2i, and so on. So here are my Gaussian integers. I guess I could have 0, that's a Gaussian integer. And then the lattice of points just with integer coefficients. So these are the Gaussian integers. Now the key observation about the Gaussian integers is this. So here's my key observation. If a is not 0, maybe I should use alpha because it looks like a is just the real coefficient. No, I'm just saying if alpha is any element in my ring that's non-zero, then the complex magnitude alpha times beta is bigger than or equal to the complex magnitude of beta. So what I'm trying to say is complex magnitude is the distance from your point away from 0, 0. So that's the complex magnitude. So for example, the complex magnitude of this integer, which is 1 plus I, is the length of the distance, to 0, 0. That's the square root of 2. Okay. Why is this a key observation? Well, if you're a non-zero number in the Gaussian integers, then your complex magnitude is bigger than or equal to 1. Because except for 0, 0, all of these dots are at least a distance of 1 away from the origin. And if you multiply by a number bigger than or equal to 1, you get a number that's bigger than or equal to 1. So that's the key observation, and that allows me to easily describe the units. So the units in the set of Gaussian integers are either plus or minus 1 or plus or minus I. These are the 4 elements that have multiplicative inverses. Okay, what are the irreducibles? Well, that's not such an easy question to answer. So instead, I think I'll just give some examples of things that are and are not irreducibles. So in this ring, 2 is not irreducible. I can take 2 and write it as a product of non-unit elements in my ring. I'll show you. 2 is equal to 1 plus I times 1 minus I. So you could expand this and you check, you get 2. And neither one of these are units. So these are not units. So I was able to write 2 as a product of 2 non-units. However, I'm going to argue that 3 is irreducible. I'm going to claim that you could not take 3 and express it as a product of 2 non-unit elements. So I could say like 3 cannot be written as A times B unless either A or B is a unit. Okay, so why is that? It stems from this key observation again. Let's suppose 3 is the product of 2 terms. Because of this observation, A and B have to be less than 3 in complex magnitude. So let me actually indicate in this dot picture, let me indicate those options that I have for A and B. So again, A and B have to be less than 3 in complex magnitude. So you can imagine drawing a circle of radius 3, all the dots within that circle are options for A and B. So in this circle, well, let me just kind of circle what I'm allowed to have here. So I could have 2, I could have, this dot. Oops, I could even have that dot. So let me include that in my circle. So inside the red circle are the points that I'm considering for A times B. But if you look at the distances away from 0, like this distance is square root of 2. This distance here, if you use the Pythagorean theorem, I think that distance is the square root of 5. I think the distance to this point here would be 2 times the square root of 2. If you think about what kind of distances you could have like this distance from 0, 0 to this point. That distance again would be root 5. So I'm going to say the only distances away from 0, 0 possible are the square root of 2. I guess I don't want a unit, so I'm not going to pick 1. But I could have a distance of 2. I could have a distance of the square root of 5. And I guess I could have a distance of 2 times the square root of 2. There's no way I can multiply 2 of these choices together to get 3. So no 2 choices has product 3. You can't do 2 times 2 and get 3. You can't do the square root of 2 times the square root of 5 and get 3. You can just look and see that no matter if you pick 2 of these choices, even if your repeated choices are allowed, so you could do square root of 5 times the square root of 5, but no matter what 2 choices you pick, you could never have product 3. So that shows that 3 is irreducible, even though I guess 2 is not. I guess from here you could also see that 5 is not irreducible, because you could take 5 and express it as a product. You could do square root of 5 times the square root of 5. So maybe I will do this point, which is 2 minus I, times 2 plus I. And then you get 5. Okay, so in this video we defined 4 new ideas that maybe felt a little familiar somewhat, at least divides did. But we've also defined unit, associates, and irreducible. All right, fantastic.